right, so what we're working on is now using integration to find volume. So what I've done on example one, I've given us a region, finite region. So we got the graph square root of x, y equals square root of x. So we know what that looks like. Y equals 0, of course, is the x-axis. And then from x is 0 to x is 4. So the first thing I want to do is just sketch that 2D region as if we were going to do area. So we can see that it would look something like this. And this is our region here that we could find the area of if we wanted. Okay. Now, the key thing to always think about is if you were going to do area, how would your rectangle be placed? You know, if you were summing up rectangles the old way. So what would the rectangle look like? So what I'm going to do is I'm going to draw one of the rectangles in here for a reference because this is going to help us when we find volume. So if we think about this, if this was one of the rectangles, let's just say right here. Right, we're actually summing up the area of those rectangles. And the area of the rectangle is, of course, the width, which here in this case is a dx, and the height, which is the height of the graph, which is whatever your function is. In this case, it's the square root of x, right? Because you can say y, but y is the square root of x. So when we go to set up our integral formula, we want an area, right? So for area, it would be the integral. Well, where are we putting the rectangles? From 0 to 4. And it would be the height times the width. That's how we would get our net area. And of course, our height would be square root of x, and our width is dx. And there you go. And then we would work it out, and of course, whatever we would get would be our area for this region. It would be actual area because so that's just a review of that. So now what we need to imagine is this region here, taking this two-dimensional, and what we're going to do on part B, it says the region is revolved about the x-axis. Make a 3D sketch. So 360 degrees about the x-axis. So picture as this, you revolve this, some solid is formed. Okay? You're revolving it 360 degrees, so come out from the board and go back to where it is. And then the way I do, how I draw that, so I usually draw it right below when I'm trying to make this 3D sketch. And I do the 2D sketch that I had before. And then I draw the mirror image. So if I'm revolving, so sometimes we'll revolve about the y. Sometimes we revolve about x. Sometimes we revolve around lines. Y equals 3. So I'll draw the mirror image. So the mirror image would look like this. And then I'm just going to try to round it off as best as I can here, so I can get an idea of the solid that's formed. So I draw the top half. Whatever I'm revolving about, I draw the mirror image because I'm trying to picture it revolving this way, and I can see almost almost a cone shape. Okay. I'm looking at it more like this. Well, that's a solid. It doesn't have any empty space in it. And what we're going to do is we're going to find the volume of it using integration. I'll show you how we'll do that. All right. So now it's kind of hard to get the, that's the toughest part, is to do the 3D sketch. Okay. So now let's visualize what happened to that rectangle. When we take that green rectangle from before and revolve it 360 degrees about an axis, remember this rectangle should be what? Is it really that wide? No. How many rectangles if we're doing area, how many rectangles are in here? Infinitely many. So they're very thin. But just picture a thin rectangle. If I revolve it like this and I make a solid, what are you forming? But think it's a very flat cylinder. Yeah, so that's the idea. So what object could you think of that might look like what I'm trying to make here? It doesn't have to be this size. But think of very thin, and you revolve it 360, you make a solid. What could that be? Something thin that's circular. How about a penny? Right? Think if your rectangle is very thin, and you revolve 360 degrees, you're making a flat disc shape. It could be a penny or a quarter. That's kind of what I would picture. So the key thing to see here is that now our rectangle, if we revolve it 360 degrees, is not a rectangle anymore. It's a disc. And a disc is what we would think of something very circular but very thin. So what I'm going to do is take my rectangle and try to make 360 degree there and kind of get that picture. That now that rectangle has turned into a disc. That very thin rectangle there is now this shape here, which it is technically a cylinder. Okay? So just to look at this, we just highlight that. Okay? So now we have this object. So all of those rectangles that we had, and you're not going to have to draw this. I always did these 3D sketches, but really you're going to be able to get all your information from your 2D sketch. So, but I'm drawing it to help you visualize what's happening. So now, if we can add up, so for instance, this cylinder doesn't have an area. Since it's three-dimensional, it has a what? How would you, the volume. So how do you get the volume of a cylinder or a very flat cylinder? Do you remember the volume formula for a cylinder? All right, so pi r squared h. So the volume of a cylinder is pi radius squared times height. Okay? All right. All right, and for right now, I'm going to call this big R, not little r. So I'm going to use big R for now. We'll see why later. All right, so let's see. So the radius, of course, is from the center. Looking at this, the height of the cylinder is actually this width here. There's the height. All right. So we'll be able to, we're going to have to convert that to the 2D sketch in a second. Okay. So if we can sum up infinitely many of these volumes, because for every one of these rectangles now has turned into a cylinder, if we can find each volume and add those up, just like we did this, we're going to get the volume. So the way volume works, if we want the volume formula, it's going to be from A to B, so wherever you're summing up, and it's going to be pi r squared h. If you can do that, then you're going to get the total volume of that figure. Just like this. From where to where, height times width is area. From where to where, pi r squared h is volume. So now, the question is, anytime you do integration, you need a dx or dy. I cannot do an integral formula without dx. So notice, on our area, the width of the rectangle turned into our dx. Now, looking at this picture, here's the height, right? The height is it a big height? Is it very tall? No, it's very thin, right? That's h. That's my h there, right? This height here. So this is my h. So the height of the cylinder, notice I track it all the way back to the rectangle. So in this case, the height of the cylinder is not the height of the rectangle, it's the what? The dx, it's the width. So think of it more as your width, okay? So this is that. So your height, in this case, is dx. Now, It's dx because we revolved around the x-axis. Had we revolved around the y-axis, we have a different situation and then things would change. We will talk about that. Okay, so if you can figure out your h and your r and your a to b, you've got it. So we're going to just do that for this problem, okay? So let's see. From a to b, so from where to where? Where does this figure start? Where does it end?
0 to 4.
0 to 4, same as your 2D. So that's 0 to 4. All right, so right now we got 0 to 4 pi big R squared dx. Now, all right, almost there. So you've got, just to make sure we understand, the big R is the radius of the disk. All right, so, and it will always be, if you use this method, your h, the height of your disk is always your dx or your dy. We'll talk about that. How do we know which one it's going to be? So the last thing we need, of course, is the radius. So here's my question. Is the radius always going to be the same? Like what I'm saying is there's not just one disk in here. We've got to sum up all these disks. So is the radius of the disk always the same length? No, because if I take a rectangle here, if it was here and I revolve, you're going to see you get a much, not that very big of a, I'd say that's a much smaller one. Okay, so that has a shorter radius. So your radius typically will be a function, okay? So let's think. So now let me track it. So radius is from the center out there. See? From the center out. The center, I mean, is where the axis is. So do you see what the radius is? Yeah, it's your radius in this case is from the x-axis to the curve, so it's square root of x. It's technically a y value, but we don't want to plug in y because we got dx. So yeah, so this is my radius. So here, I go here, and I'll show you how I can use the 2D sketch. So my radius is always measured from the axis of revolution to the furthest point, okay, to where does the rectangle touch. But it always is going to go from the axis of revolution to the furthest part of the rectangle. So the radius, I like to put that, how it's measured. So just to make sure that we're clear on this, so when I'm measuring my radius, it's measured from axis of revolution to furthest point of rectangle, or furthest edge or whatever. Okay? Your height of your cylinder is the width of rectangle, always. Okay? So, he's exactly right. So I could put y in here, but I don't want to put y because we have to take the integral with respect to x. And so what did Elijah say? He said the radius is square root of x because y, that's your function. So you have to do some substitution there. All right, and then we get this formula. Now, that's it. You can work that out. You'll have the volume of that. Now, one thing, so here's your volume problem. So this is what, it looks like it takes a long process, but it doesn't. Your limits you should know pretty quick. You're always going to have a pi in every problem. This is pi r squared. The way your rectangle is constructed, you'll know whether it's dx or dy. And then the hardest part is going to be for you to figure out what's the equation of your, or what's the formula for your radius. What can I take out of this integral? Pi, always. So just, I would take pi out. Okay? All right. Go ahead and work it. What happens when you square root? It's going to be a quick problem. And we will have the actual volume of that figure here. So we've got, for volume is pi, integral from 0 to 4, square root of x squared, dx. And if you just work that out, multiply your answer by pi, you'll have the volume. So if you don't get pi in an answer, you probably left it off. You're going to have to make sure you put your pi there. Okay, so let's see what we get. Pi integral from 0 to 4 of x dx. Antiderivative of x is x squared over 2 from 0 to 4. This is going to work nicely because now we don't have to worry about plugging in a 0. So we plug in our numbers, so pi times 4 squared over 2 minus pi times 0. 4 squared over 2 is 16 over 2. We get 8 pi is the volume of this solid. Okay? So you should get it. Okay, so before I move on to example 2, I want to kind of generalize to make sure that we understand from the 2D sketch what the 2D sketch is going to give us. But do not forget this. This is how I'll always refer back. You're going to say, well, I don't know how to get big R. Big R is measured from the axis of revolution to the furthest part of the rectangle. Your h is the width of the rectangle. It could be. You're going to see it may not be. It could be a constant. Okay? Could be a constant. It depends on the figure we have. Typically, it will be a function of x or a function of y. We'll do another one and see. What are you asking me?
So like a big constant is just a line.
Yes, that's exactly right. It could happen.
If it was a line, would we have to go through this, or could we just?
You're gonna. So here's why I'm introducing it this way. We've got to have two methods. So I'm trying to make big R so your big R is the same here. You see? If I change it to here, it's not going to make sense because here you're going to have two radii. You'll understand why I need a washer. When I'm saying a washer, if you've worked on cars, like a washer, the tool, right? Not a washer like the washing machine. It's not washing machine method. This is more of a donut, very thin, flat donut. So here in washer method, your big R is the same calculation that you would make here. But then you'll have a little R that you'll have to find. I know you're excited. I know you love binge watching Netflix, but we just got to get through episode 1 right now, okay? And then we'll talk about that. But yes, I mean, I can't answer your question with a right because it depends. And you'll see sometimes big R could be a constant. But here's what I can tell you. Big R is always measured from the axis of revolution to the furthest part of the rectangle. You can figure that out, and you're always going to be able to get your big R. Sometimes so you got to look. Is what my rectangle going to? Is it a curve or is it, like you said, linear? Like a horizontal line? That's going to be the question. Okay, so I'm going to leave those two up there. I'm going to erase this problem for now. We'll set up another problem. Actually, let me just let's do one more with respect to x, like this, and then we'll, okay, so example 2, we're going to do the same thing. So example 2, given the region bounded by y equals, I'm just going to call it f of x equals x squared, y equals 0, x is 0, x is 1. A sketch the 2D region. So you're going to always want to make 2D regions, and with your rectangle, put a rectangle in there. All right. Part B, the region is revolved about the x-axis. Make a 3D sketch. All right. And I'm going to also make this note. Your rectangle is always perpendicular to the axis of revolution. So, however you're revolving, whatever you're revolving about, your rectangle should always be perpendicular so you get a disc. Otherwise, you won't get a disc. Right? So, we'll make this 2D sketch. So, x squared from 0 to 1. So, we've got this shape here, bounded at 1. That's your 2D sketch. I used to skateboard back in the day, and we would call that a half pipe. That's actually a quarter pipe, never mind. That pipe would go back up, I guess. I know I'm going to revolve around the x-axis eventually, so I'm going to go ahead and place my rectangle perpendicular to the axis of revolution. From there, I should be able to know what everything is. Okay. For instance, what are my limits? What is my radius? And what is is it dx or dy? Okay, so we know that volume is going to be pi from A to B, big R squared. And in this case, it's going to be dx because we can see that the height is the width of the rectangle. And the width of the rectangle is going to be always dx or dy. So now all we got to do is know our limits and what's our radius. I like to make a 3D sketch just to kind of picture it, but you're going to see you don't really need a 3D sketch. Because the way I've referenced your radius is measured from the axis of rev to the furthest part of the rectangle. So what I would do is I would just come over here and say, oh, okay, well, the radius should be from the x-axis to here. That's my radius. But what is that? Okay. All right, I just did a 3D sketch just to see what it looks like, but you can tell it's, it's kind of like I don't know, almost like a cone, okay? Solid cone. All right, so what's the radius? So if I measure from the x-axis up, again, that's just a y, you can see. So your radius is a y, and what does y equal in this case?
X squared.
X squared. You set that in. What are your limits from where to where? 0 to 1. So it's going to be x squared dx. Okay? All right. So go ahead and see if you can finish that and get the answer. It's going to be fairly quick. 0 to 1 of x to the fourth. What did you get for the antiderivative?
X five.
X to the fifth over 5, 0 to 1. Well, you should have just got 1/5 pi, or pi times 1/5, or
Yeah.
pi over 5. The volume. Very small figure, okay? So I don't want you to always think that we're gonna revolve around the x. I'm gonna give you a problem now. Hopefully it's fairly simple. We're gonna revolve it about the y. Now look, a couple of things. It will not always be, it will not always be as simple as that the radius is a y value. Now, how do I know it's a y? Because anytime I measure from the x-axis to an arbitrary point, that's y. Because it's vertical. I'm measuring from the x. Had this been our curve, right? Right, here's our rectangle, then it would be from the x-axis to here is a y, but it will always be 1. Then we would have just got a big cylinder there. Okay? So I just want to make sure that we're clear on how do I know that it's a y. So now I'm going to change this up a little bit and give you a different type of problem and see if you can make this the 2D sketch. The 2D sketch is what is important. You know, so those three highlighted things are important up there. Okay? How do you measure big R? From the axis of revolution. The rectangle is always perpendicular to your axis of revolution. That tells you whether it's dx or dy. See, if my rectangle is vertical, it's dx. If my rectangle is horizontal, then it has to be dy for the height of it. Change in y. Okay? All right, so here we go. Next problem. And in terms of, what do you notice about the integration? Once we get it set up, it's fairly easy. We're not working, we're just trying to get the idea right now. So example 3, given the region bounded by f of y equals y, x is 0, y is 0, y is 2. Find, let me say this, all right? The region is revolved about the y-axis to form a solid. All right, part A, make a 2D sketch with rectangle. Part B, find the volume of the solid. Notice my function is in with respect. What variables here? X. This is x equals y, or y equals x. Okay? If you do f of x, then that's a y. If you do f of y, then that's an x. So this is the same as saying x equals y. But I want you to understand this, you're going to need it to be with respect to y. Okay, so let's look at this. X is Y, that's this line. But I'm bound to get by X is 0. What's X is 0?
Oh, the X, I'm sorry.
The Y-axis, right? X is the Y-axis. Y is 0 is here, 2, Y is 2. Okay? So this is your region. Your region should be a triangle. What happens when you revolve a triangle? You get a cone. You really don't need calculus for this. Okay? So first, you're going to have to be able to understand that from those equations that this is your enclosed region. You're looking to see what it encloses. You may have to draw a whole bunch of lines now, okay? Because you have to have a finite region to have a solid. You can't have an infinite region. Now, that's a different story. We'll come back to that later. All right, my rectangle always goes how? Is it going to be vertical or horizontal? Horizontal. 3 height points. This should always be on the top of your paper if you're going to do this. Rectangle is always perpendicular to the axis of revolution, so it goes in horizontal. That rectangle tells me everything I need. If I can draw that rectangle, then I'll know what my radius is and I'll know what my height is. Okay? So now, let's look at this. It's going to be, I'm going to go and draw the 3D just to have it, but you don't really need it. There you go. Okay, we have a cone. All right, a legit cone, a real cone. This is not like a made-up cone. This is a cone. Okay, so you could just use. We'll see what the volume of a cone is in a second. See if that makes sense. All right, so now let's see. Volume pi. Now in this case, it's y limit, so I usually do c to d, big R squared, and in this case, it's going to be dx or dy. Dy, because that's the width of the rectangle, dy. Now, the question is, what's my radius? Your axis of revolution is here, so you always measure your radius from the axis of revolution to the furthest part of the rectangle. Well, let's see. From the y-axis out is what type of measurement? From the y-axis out is labeled as what? X. So your radius is x, but you can't sub in x, right? Hang on, because look, it is x. It's always an x, but I can't sub in x because it's with respect to y, but go back over here. X is y, so I put y in. Since x equals y, then that's what I put in. All right, what now, my limits, since it's dy, should be y limits. What are my y limits? 0 to 2. Y quantity squared, dy, and then you work it out. And that's how you work it with respect to y. No different. Okay? So let's see. Pi times antiderivative of y squared. Okay? 0 to 2. And we get pi times 2 cubed over 3 minus 0. So we get 8 pi over 3. All right, let's see if that is the volume of a cone. So the volume of a cone is 1/3 pi r squared h. Okay. Radius would be here of the actual cone, which in this case, if this is 0 to 2 this way, this has to be a 2 here. Radius has to be 2. And the height is 2. 1/3 pi, radius is 2, height is 2, you get 8 pi over 3. That's why these formulas are a little bit easier. But I just wanted to show you that it was equivalent and just get you comfortable with it. So all I'm going to do now is summarize what your 2D sketch tells you for with respect to x or with respect to y, assuming that we always form a disk. And again, your disk here would have went like this, would have revolved it this way, so it would have been flat. That's a bad. This is not the easiest thing to draw, by the way. You don't have to, and that's the thing. If you just use this properly, you don't need this. Just think what it's gonna look like, but that's it. So now to summarize what we've looked at today, if I'm revolving about the x-axis, so if this is my region, so if this is my region here from A to B, and I have a vertical rectangle, so if we're revolving about the x-axis, volume is pi A to B, it's gonna be dx, and big R squared, all right? And if we're revolving about the y-axis, rectangles like that, volume pi c to d, big R squared dy. Okay, we're revolving this way. Revolving about y-axis. All right? That's just the introduction. It gets a lot deeper than this. We're limited to the problems we can work because we need, you'll see why we need the other method in a second, in a little bit. And then we'll look at that, all right? So I'm gonna stop for there. That's the introduction. You have the rest of your 6-1 to finish, and then we'll finish this, or we'll do another big chunk tomorrow. I was just gonna wait till tomorrow to add on. We'll do a refresher problem, and then we'll do more. So we'll start this homework tomorrow, okay?